1. Hello, welcome, good afternoon, everyone, to this week's Zoom for Thought, during which JJ will tell us about how pointless topology is. Take it away.
Hello, everybody. So thanks for coming. It's my talk, and yeah. So this is a talk about something called pointless topology, which is an alternative for topology that does not hold points as fundamental. So let's start by remembering what a topology is. So just briefly, so some of you may have seen this before, but that's okay. So we'll start with a topological space, which I'll abbreviate as TOPSPA. We'll call it X, is a set, and the elements of this set are called points. With with a collection, let's call it a collection, omega of X, which is going to be a subset of the power set of X. So excuse my bad script P, but this is the script P we're getting today. And this collection is going to be called, we're going to call this the collection of open sets, right? Yeah. And so it has to satisfy some axioms. So there's the axiom of finite intersection, right? So if I have UI intersect ... intersect, or well, maybe I'll say U1 intersect UN. So if UI are in omega of X, then this is in omega of X. There's the axiom of arbitrary unions, which is very similar, except instead of course, finite, we're going to have arbitrary. So I'll just write that down. This is going to be in omega of X if all of the UI are in omega X. And then finally, the last axiom is that the empty set and the entire set are in our set omega X, and then omega X is, so this, we just defined a topological space, and omega X is called the topology. The topology. So this is somehow this definition and this concept is sort of due to mathematician Hausdorff approximately 100 years ago, and it's been, I think, the focus on open sets has been something, right, that has really been influential in mathematics. So some examples that we'll think about the real line, and then the topology is just, open balls and their unions, right? So an open set might look something like this. Another example that might be familiar to a lot of you, but not familiar to some, is if I have a finite set of points and I take the complement of the finite set. So R omega R would be complement of finite sets. And so, yeah, so while we love topological spaces, So I just wanted to recall some stuff. And so what are the things that are problems with topological spaces? So let's shift gears for a second. Just some quick bullet points. So when we think about topological spaces, we have many things that are weird counterexamples. If you want more information on this, you should watch Tanny's talk from last quarter. Another problem, which some might consider more of a problem than others, is that there's bad category theoretic behavior. Behavior of these things in general. And so normally when people are studying topological spaces and they want to use category theory, they restrict to a special class. And then this third thing, which may apply to the least amount of people here, is, well, there's sort of two things. There is such thing as spaces without enough points. So I don't want to talk too much about these, but they come up when you study maybe things like algebraic stacks or something. And then there's a sort of similar thing, which is topological spaces require the axiom of choice. When in particular, there's a theorem called Tikhonov's theorem, which uses the axiom of choice. So I expect these 2 points are maybe not reasons people, like a lot of people don't mind these 2 things, but the people who came up with pointless topology care about these things. And that's how it sort of came about. Is there, you want to come ask a question where you can?
I'll ask the question so that they can hear.
Where the, okay, there's a question from the room.
Hi, JJ.
Hello.
I have a question. So is it true that for Tikhonov's theorem, like the axiom of choice you have to use is not actually the full thing?
Oh.
And do they care about that? So do they care about any level of?
So the people who think about pointless topology definitely care about any level of choice.
Okay,
I don't
okay.
know if it's the full, if Tikhonov's theorem
All right,
requires.
sweet. I think Greg was nodding his head. It's probably the open filter, right? Is that?
It's online. It's on the YouTube channel.
Oh, it's already online. Yeah, we've had this. I think I literally have had the same question and conversation on another Zoom.
Okay,
talk.
so
We're
in
good.
that
Moving
case, if you want to know more about this, watch Greg's talk.
What's all the other ones?
So when topological spaces were first popularized, it was a perspective shift. And the perspective shift was to focus on open sets. And the perspective shift that I want to take in this talk is open sets are so fundamental that they don't even need to be sets. We can just forget about the sets that underlie them, and the open sets are the only things we need. So we don't even need points. Okay, and so to carry this plan out, I'm going to have to make a few definitions. Of course, if there are any other questions, feel free to speak up. So let L less than or equal to be a poset. So this is a partially ordered set. So the things in this set are going to have some order, and maybe I'll write maybe I'll write my set as like some dots here, just for, you know, example purposes. And then I can write some arrows. And so if there's an arrow between two elements in this set, then that means that, you know, this one is less than or equal to the other one. So an arrow means they're less than or equal to. And it'll be a partial order. So something maybe like this. And so this whole time we're going to be operating in sort of the poset sort of area. And what we're going to do is, if I have a subset of L, I want to declare an upper bound for S is an element U in L such that, well, S is less than or equal to U for all S. So let me do a quick example. If this is my poset and I have this set of points right here, so the set is this one and this one, here's an upper bound. This is one upper bound. Here's another upper bound. Here's another one. Here's another one. My partial order is going to be transitive, I guess. And so the point is, upper bounds are not necessarily unique. And sort of this is in an analogy with actual, like, less than, sort of on something we would be more familiar with, like a real line or something. And then likewise, we'll say a lower bound. That's just the exact same definition, but with lower bound. That's for all S and S. Okay. Now, yes, question.
So you're defining it upper and lower bound to different because it's
Yes. Well, in this post set that I've written,
yes, right.
they do not always exist. That is correct. In this next definition, or in two definitions, okay, we're gonna do some more definitions, then they will exist. But yes, this is good. So, okay. So let's do another definition. An upper bound U for some set S is a least upper bound. Yep. If let's see, U is less than U prime for all upper bounds U prime. So maybe pictorially, I had these two elements as my set. And then this would be a least upper bound. But these three, they're upper bounds, but they're not least upper bounds.
Just to be clear, it has to be an upper bound as well, right?
It has to be, yeah, it has to be an upper bound. Yeah. So this is an upper bound for these two guys, and it's also a least upper bound. Okay. And then again, likewise for lower bound. So we have L is greatest lower bound. And then, you know, same thing if L prime is less than L for all lower bounds L prime. Okay. And so let's see. So this definition, okay. Yeah, sorry, okay. So what we have is this definition of least upper bound and greatest lower bound. But so for our purposes, I don't want to have to say least upper bound over and over again and greatest lower bound. So least upper bound is going to be called the join, and greatest lower bound is going to be called the meet. And so we're going to write it this way. So if S was our set, so S is their set, the join of S is going to be notated like this, and the meet of S is going to be, this is meet with 2 E's, by the way, and that be right, U and L in the previous definitions. And so why is this symbol like this? This is supposed to inspire you of thinking about the union, and this is supposed to inspire you of thinking about the intersection, but it's not the union and the intersection. So that's what join and meet are. And so I said we had a bunch of definitions, and I wasn't lying. So L, which is our poset, is a lattice if every 2-element subset has a join and a meet, and L is a complete lattice if every S, so every S has a join and a meet. And so again, this idea is sort of mirroring, much like we had before. We have somehow the join and meet are union and intersection, and then we can always take, if we have 2 sets, we can always take their union and we can always take their intersection.
Out of curiosity, you really mean every, you don't just mean every set is bound above and below.
I think I do mean every, yeah, because I think part of this is that every set is bounded above and below. So yeah, so that's yes, that's correct. Maybe a picture is good. So if I maybe I'll write, I'll put this poset. Let's say that less than or equal to goes down. So anything that's higher is less than or equal to the other things. And things that are the same row, can't be compared, say. And so I'll just connect all of the connections here. So if I have a point A right here, and this is point B, what is, let's see, what does A meet with B? So it would be, well, so somehow there is none, right? Because this guy right there is a lower bound for A and B. But so is this guy. And these two can't be compared. So there does not exist a meet. So I want there to be a meet. So I'd have to, maybe I'd have to delete an edge right here. Oh, it didn't delete the whole edge when I erased. Sad. Very sad. So now A and B are going to have the greatest lower bound of the meet right here, right? And you know, you could say something similar for this is an upper bound, but unless I delete some edges here, you know, maybe I delete this edge, and this edge, and this edge. It's not going to be a greatest. It's not going to be a greatest, or it's not going to be a least upper bound unless somehow there's sort of only two of these guys. But this guy is easily the least upper bound of these four. Okay. So that's some lattices, and so and so now I want to sort of remember what we were talking about with topology. So this actually, I want to write this as a complete lattice. And so first of all, we need to think of it as a poset. So how can we think of it as a poset? Well, this guy is a set of subsets. So this is a poset ordered by inclusion. Right. And then now I can always take the union of two subsets and get another subset. And I can take the intersection of two subsets and get another subset. So omega x is a lattice. Importantly, I needed to use the axioms of a topological space here because I wanted that the union of two open sets is an open subset in here, and the intersection of two open sets is also an open set. And so what we do now is we now need to think about well, so under this identification, so it's a lattice, and then the meet corresponds exactly, basically, by the construction we did to intersection, and the join corresponds to the union. And so now we want to say this is a complete lattice. And so if we remember our axioms, let's see, they're back here somewhere. We have that arbitrary unions are in our lattice. So given an arbitrary subset, so we have arbitrary unions imply that all joins exist, right? And in this case, as Maki asked earlier, each subset actually has a least upper bound. There is a single thing that's the union, and it always exists. And then so we need to worry about intersections because our axiom only says that, you know, if we intersection a finite number of open sets, it'll be open. But what we can do is, so for meets, so if I wanted to say the meet of ui over I and I, where I is some arbitrary index set, well, what I can do is I'll define that to be, I'll take the intersection of all of them, and then I'll just take the interior. So I just take the interior, and this will be a complete lattice. Moreover, because of our arbitrary union axiom, we have the following, which is that we have, if I have a U and I intersect that with an arbitrary family of other sets, VI, oh boy, this looks like UI, VI, with lots of U's and V's here. Oh dear. So let's say U and VI are open sets. So if I intersect those, this is going to be the same, I guess by De Morgan's laws or something, as if I take the intersection with each individual one of these and then take their union at the end. So if you like Venn diagrams, you can write this out as a Venn diagram. But so this axiom, which is not satisfied by all complete lattices, is going to somehow be the thing that's going to make our complete lattice, quote unquote, topological. So let's make our sort of crowning definition of this talk, which will be, we're going to define a frame is a complete lattice we'll call it F, that has the distributive law. That has in particular has this distributive law. Maybe I'll copy and paste it so we don't have to write it again. So that's what a frame is. And our idea is somehow our frame we should be able to study this instead of studying a topological space. And so somehow, so if a frame, so first one maybe term, if a frame is omega x for some topological space, then F is spatial. There do exist frames which aren't spatial, and those kind of get weird. So somehow the idea is this, and so the point of this definition, if I may say so, is that it makes no reference to points. We have all of the information about the open sets, and we have none of the information about the points. And like I was saying before, the point is that this pointless approach can kind of get us the same sorts of things. There's one sort of slight technical thing which I'd like to correct, which is maps between topological spaces. So f of y, f from x to y is a map of topological spaces. It's a continuous map. So when we get a map between omega x and omega y, but it's actually, the map is in the wrong direction. It's a map, maybe we could call it f star, from omega x to omega y, which takes a subset u in y, right? U will be in y, and it goes to f inverse of u. This is the sort of important thing about continuous maps, is that continuous maps, the pullback of an open is an open. But this is a little bit inconvenient for us because somehow we want, we want maps of frames to sort of go in the same direction as the maps of their associated topological spaces. So what the solution to this is, it's sort of cheating, but what we're going to do is we're going to take something you might call like a formal opposite, or formal. So we're going to define something called a locale, which is a frame. But maps of locales, but a map of locales so let's see. I should define this maybe with some letters. So if I have two locales, F and G, a map of locales is a map from G to F of, of posets or something. It's got to preserve the order. Or maybe it's a map of lattices. Let's say of posets. This might not be technically true, but think of it as like an order preserving. And so the point here is that we have the right thing, we just have the wrong direction for the maps, and we actually give it a different name, but you should think of these two things, locales and frames, as just being the same thing. And so for now on, I'm going to use the word locale. And so elements of a locale,
just to be clear though, when you say locale, you really just mean frame, right?
yeah, more or less. I mean frame.
We could just as well call them a map of frames.
Yeah, well, no, okay.
Like a definition, a map from a frame. From a frame, you have two frame G and actually function
From G to F that satisfies the things. We could, but that's not what the literature does.
Right,
So this is what I'm doing. Yes, yeah. So like, if you want to confuse locale and frame, that's fine. But yeah, locale is somehow the word that I want to use. And so we think of so maybe the picture is to think of elements in a locale as spots, patches maybe, or a word that people in topology always use, neighborhoods. So, right, we have that real line. And then the thing that I use to geometrically represent that real line, or topologically, I guess, I don't know, is I literally have the set of, you know, open balls and then unions.
In particular, this heuristic is really for Hausdorff.
You need not be Hausdorff here. I think somehow these are very interesting when things aren't Hausdorff. But I don't want to say too much about that because I want to talk about different directions. So I will state one theorem, but I need one more definition, which is a sublocale. It's really an isomorphism class of, but just think of it as a subset of a locale. Which is a locale under the induced order. And so what that's going to be, so again, our example is the real line. And then I want to take a subspace of that real line, which is an interval, say the interval from 0 to 1. And so how do I think about the subsets of a topological space, or not the subsets, the subspace of a topological space? There's something called the subspace topology, which is all of the open sets are, you know, things which, sets which are intersections of open sets in the big guy with the little guy. So like this set would be open in the subspace topology. So what we're doing here is the sublocale corresponding to this is for every open in the subspace, pick one set, pick exactly one set U in omega of R, such that U intersect this interval, maybe we'll call it I, is the subset that we started with. And then this collection will form a locale.
Is your definition of frame, i.e. locale, built so that a single element of the locale gives rise to a sublocale?
Yeah, it should.
Okay.
I think. Yeah, I think you can take all of the. I think you could take just all of the things that are less than that in the order. But so it would be a little. You might have to pick one out of a class of them. Something. Somehow this construction is also kind of it's under the hood. It's like a quotient. So we have to pick a representative. You might be in my, but this is my example. I think maybe somebody in.
You're always allowed to pick a single element.
Yeah.
That's where it is quotient.
Yeah, really, this is a quotient construction. I'm sort of just saying this for illustrative purposes. What was your question, Navik? Oh no. Okay. So yeah. So this is this is a sublocale, and if frames and locales are different in your mind, this is a quotient frame somehow. But I don't want to get into that again. That's a little bit of a technicality, not so important. And so, as far as I can tell, in some ways there aren't that many uses for these pointless spaces. So, in that pointless, man, I was gonna say this joke, and then the audience got to it before me. Yeah, man. But because I don't know, I myself am fine using the axiom of choice and all of that. But there is one theorem that is pretty cool about these guys, which is the following. Any locale has a smallest dense sublocale. So if we think about this, if I'm thinking about sets or topological spaces, it's pretty easy to come up with two dense sets who have intersection 0. Right? So our set difference Q, all the irrationals and the actual rationals, they're disjoint as sets. Yes. Yeah, so I think there's a way that you can do closure of these, and it would be like its closure is going to be the whole space. I think that's the best way to do it. So an example I shouldn't say this. Yeah, no, it's I don't know if it's completely clear, but so if you think about, there's an example that I don't know if everybody knows, but if you think about the topological space of a scheme, this has a point whose closure is the whole space. And so somehow this, like this point, is itself a sublocale, and that's its closure is the whole space. So I think like if you let's see, I don't know what the right way to say this is, but I think if you look at what the sort of poset is in that in that situation,
yeah, I suppose you could use the topology definition for locale that are spatial topology.
yeah, it will be.
But for non-spatial,
but like there is sort of a localic way to do this.
I think you got a column here.
Yeah, it's like something like this. Yeah, you can take interiors of these guys, but it's like, yeah. So sorry about this, but yeah, we are almost done. Yeah, no worries. So in locale world, R mod Q intersects Q will be dense. And if you think about this, R mod Q, like if you think about an open set in R, say an open ball, it's going to, like, you're going to be able to tell apart somehow, tell apart the open sets, just by, say, what happens on the irrationals, or just by what happens on the rational numbers. So somehow the locale here, it can tell apart. It somehow it's I don't know. I don't know if I know how these things work as good as I wish I did, but you can actually tell you can, like, the fact that there are elements in Q that are arbitrarily close to elements in R mod Q means that when you're thinking about the locale, it sort of sees those somehow. And that's sort of the whole point of all of this pointless topology. And so and somehow the last thing I'm going to say is that one can actually one can understand the Banach-Tarski paradox. I'll be very brief about this. So the Banach-Tarski paradox says that you can take finitely many pieces of one ball and then sort of disassemble them and reassemble them into two balls, and those pieces are going to be using non-measurable sets. But these sets are disjoint. Somehow, a similar thing happens with locales, with R mod Q, and Q happens to these non-measurable sets. So when thought of localically, yeah, when thought of pointlessly, such sets will not be disjoint. So I guess the idea is that locales will see somehow all of the possible open neighborhoods of one of these pieces that contains any part of the other one. Yeah, so somehow this is, so one of the resolutions of the Banach-Tarski paradox is, like, we see that the sets used in the Banach-Tarski paradox are non-measurable, and we say that no, it's actually a good idea only to consider measurable sets. Whereas this approach is saying it's, if we, rather than considering the sets at all, if we consider the locales, and somehow all of the possible open sets, then we can't do Banach-Tarski paradox. A question in the chat, sorry. So of the things that so like, I didn't really hamper too much on the lack of using the axiom of choice. I think that is sort of historically one of the things that people really mostly study these for, and I think people in like logic or constructive mathematics will still study this. These spaces that are quote unquote don't have enough points. These sort of, those are another thing that I sometimes people reference with talking about locales, but I don't know how often they're actually used for stuff like that. Yeah, if that's an answer to the question, if that's any help at all. Yeah, no, I'm done.
All right, everyone, let us thank the speaker.